Okay, so the talk's a little different than the title. We're really going to be talking mostly about North Pacific sea level changes, how they're related to wind forcing, and how we might interpret, using tide gauges and altimetry, sort of the longer history than just from the altimetry period. So, as Annie presented yesterday, here's the map of sea surface height trends from 1993 to 2009 from a VSAT. And of course, the main points of interest here are the high rates in the Western Tropical Pacific and the low rates in what we tend to call the PDO region along the North American continent. So how are they connected, and what are the drivers for those changes? How can we relate those changes to some of the dominant Pacific climate indices, that PDO, SOI, and SO indices? So where we start is in the Western Pacific, and there are about 12 tide gauges that are right in this hot spot of sea level rise. 3 of them go back to about the mid-20th century. Most of them go back to about the 1970s or so. So from these 12 tide gauges, we can reconstruct then sort of the average sea level in that region. And you can see that the high sea level rate here is associated with this increase in the trend, which began around 1990 or so. And prior to that, it was rather flat without much change in sea level. So that's the sort of the big inflection point there. If you look at the winds during that same time period, so we're using ECMWF ORA S3 winds. So plotted on top of that the sea level trend map are the wind trends. And you can see that during this period there was a strengthening of the trades in general, sort of upwind of the red patch here, a strengthening of the anticyclonic wind feature in the North Pacific. The Atlantic was fairly quiet during this period, except for the North Atlantic. And the question is then, how do these trades go about leading to the pattern that we see? So a high-resolution POP model was run by Matt Maltrid at Lawrence Livermore Labs, the National Labs in Los Alamos. And so again, here's the trend from a VISO. And this is the reconstruction of the sea surface height trend using those ORAS3 trends we saw before. So just by this trending wind stress, you were able to get most of the features you see in the SSH trend in the North Pacific. So the high rates in the Western Pacific, low rates, although not as accentuated, on the Eastern Pacific, and even some of the higher latitude features show up as well. So, as Andy pointed out, as a lot of people have looked at, there have been other studies as well that have looked at wind forcing. Pretty clearly, it's the low frequency changes in the trade winds which are driving this patch, which has persisted for the whole altimetry period. And looking at the tide gauge records, we know that it's been a change from the earlier, last half of the 20th century. So, tend to think, I know Annie mentioned yesterday that you sort of tend to look at these things in connection to Argo and say, okay, well, this is a steric height effect. This is thermal expansion of the water column. But from an oceanographic point of view, obviously there's a lot of dynamics associated with this feature, more than just a steric adjustment for density. So the model is a nice way to look at all that. So these are the surface currents associated with that trending wind, and these are the trends in the surface currents. And so you can see south of the equator here, the south equatorial current is picking up in speed. Other features of the equatorial circulation are changing through that period. If you look deeper at sort of the base of the thermocline, the color is sort of the change in the thermocline depth. The equatorial undercurrent is picking up, is accelerating as that sea surface height gradient is increasing across the Pacific. As you're building up water in the Western Tropical Pacific, there's more through flow. There's a pressure head that's driving flow through to the Indian Ocean. And this is a measure of that just trending over the whole period on top of the annual cycle in the model. If you look at the stream functions, this is now looking east to west. So northern hemisphere, southern hemisphere is the equator. These are the contours of the stream function. So what's happening is the meridional overturning circulation is getting enhanced with this wind forcing. So increased upwelling and increased diversion with flow toward the poles at the surface. So quite a bit happening with this wind change, not just sea level. When you see that sea level pattern, it's a nice indication of something happening along that waveguide, which is causing a lot of changes in the circulation of the tropics. So how to relate this into these indices? So we know that it's forced by the winds. I'll show in a little while the winds aren't as solid as you might think. So we'll take that sea level, average sea level from the tide gauges that we got, and subtract out global mean sea level. So that's the black curve here. So that thing that looked like a flat period and then acceleration turns into sort of a flat period and then a dip, is really how to interpret it more. And that lines up nicely with the sort of the main Pacific climate indices in the Pacific. So the PDO is in blue, regressed against it, and the SOI, Southern Oscillation Index, as well. So either one of those during this time period since 1950 do pretty well. Correlation squared of 0.75 for PDO, 0.7 or so for SOI, in accounting for this change, because both of them are a measure of the strength of the trade winds during this time period. So that's all outlined in a paper we just finished with Phil. It corrects some misconceptions that were in an earlier paper where I kind of came out strongly against that relationship, but that's since been corrected. And it puts us in harmony with some earlier work by Ming Feng and the group at CNES. So if it's related to the PDO, then the PDO must have an expression of the wind, tropical winds changes in the trade wind region. And that's certainly true for regressed PDO on top of the NCEP1 winds. You can see that it has a strong expression at the equator, right where we had that trending wind pattern in the ORAS3 winds. Also some off-equatorial extensions to that, particularly associated with what we characteristically think of as the PDO forcing in the North Pacific. Okay, the problem with these winds is that, so if I take a box here in the tropics and sort of average the zonal trade winds, you get very different results depending on the reanalysis product you've looked at, so the wind product you're looking at. So this is sort of the ECMWF winds we were looking at, flat winds for the period before 1990, and then picking up. So this negative changes and strengthening of the trades. NCEP was quite different. It was trending over the whole period, and then it flipped. And so actually, the NCEP winds are a little closer to what we actually see in the sea level, right? Because in sea level, what it looked like was sort of a flat period for quite a while, which is going against global sea level. So it wasn't rising as fast as global sea level in the Western Pacific, which meant that the trades had to be decreasing over that time period to account for that. As we flip the other way, and now the Western Pacific is rising much faster than global sea level, there has to be a trend in the other direction, and that's what we see. And actually, neither is quite right. When we run these winds through that POP model that I showed you before, ECMWF actually does better after 1990 than NCEP, but NCEP does better than ECMF did before 1990. So there's some work that needs to be done to bring these all into harmony with the tide gauge data sets. So you can think of the PDO and SOI sort of interchangeably then as a way of coming up with an indice for the trade wind forcing and the sea level change that you'll see in the tropics. And SOI and PDO do pretty well. They do pretty well since 1950, and that's the time period when they both are well correlated with one another. But over the longer record, and particularly before 1950, they diverge quite a bit. In fact, there's no correlation between the two indices before 1950. So we don't have, okay, so again, this is that just showing that we can correlate these two indices to the Western Pacific sea level after 1950. We don't have anything in the Western Pacific before that period to really nail down which is better, SOI or PDO. We can go along the waveguide. Ming Feng in particular has shown that going right down the waveguide to Fremantle, southwest Australia, is a good, or correlates well with changes in the winds and in the tropical Pacific. And when you do that, you find that the SOI more closely matches Fremantle sea level over the whole time period. And PDO tends to degrade primarily because it no longer captures the variability before 1950. So kind of what we're coming to is that if you want to characterize this pattern, the SOI turns out to be a much better indicator than the PDO. Even though it sort of has a nice characteristic PDO pattern, there's been a lot of papers lately that have noted that these are associated with PDO shifts. But really, it's the SOI, which is a more direct measure of tropical Pacific winds, with it being a pressure gradient along the equator, than the SOI, which is a measure of SST at higher latitudes. So that's somewhat circumstantial at this point. We only have one tide gauge here, and it's not even in the Western Pacific where we're looking at. So Phil's been looking up the, what we'll call the PDO regional on the North American continent, and he'll go on to tell you how this plays out in that region.
Okay, so as Mark just told you, this is kind of Act 2 here. I'm going to talk about recent rates of coastal sea level change in the Northeast Pacific. And the first thing I'm going to tell you, and I'm going to try to relate that back to what Mark was telling you as well. First thing I'm going to show you are 20-year rates of change from Fremantle and San Diego in sea level. These are millimeters per year. And what you get from looking at this is you get the idea that there's a historical relationship that when Fremantle sea level is rising faster, then San Diego sea level tends to be rising slower. And vice versa. And so this relationship suggests that there may be some type of zonal volume redistribution across the Pacific, and there may be a common forcing between these two locations. So this is basically what Mark just showed you. So this is just the North Pacific sea surface height trends from altimetry with the global mean trend removed. This is what Mark was talking about, and then I'm going to focus here up in the Northeast Pacific. And what I want to point out is that this pattern, this kind of horseshoe pattern here in the trend map is very similar, as Mark was just saying, to modes of sea surface temperature variability that is defined to be the Pacific Decadal Oscillation. These also show up in models in sea surface height as well. And so if this pattern here is part of the Pacific Decadal Oscillation, then you would assume that in previous decades prior to altimetry, you might have a swap in sign. You might have positive trends along the coast and maybe negative trends in the interior. And so what I'm going to do is I'm going to focus on the coastal sea level here and see if we can understand a little bit about that pattern. So these are coastal sea level, annual coastal sea level values from Bomersky et al. In 2011. And we have San Diego, San Francisco, and Seattle. You can see that the rates during the recent time period are actually fairly flat, which is consistent with the altimetry. But if you look at the rates during this kind of middle of the 20th century time period, which are given here, they're actually greater than the global mean rate during that time period. So if you say like 1.5 millimeters per year there. So you have this sort of inflection where you have rates that were greater than the global mean rate and then into a flatter period. And the authors here said, well, that's related to large-scale changes in the wind stress curl over the Northeast Pacific, which is in turn related to a phase change in the Pacific Decadal Oscillation. And that may be true for the interior part of that pattern, but if you just look at the PDO index compared to the sea level in this region, there's really not much of a relationship. This is a low-pass version of the PDO index, meaning variability longer than about 15 years. And then you also have the same for San Francisco sea level. And you see this positive phase, negative phase, positive phase in the PDO, but it's just not there in the sea level, in the coastal sea level. So then the question is, if PDO dynamics are not driving the long-term variability in sea level in the Northeast Pacific at the coast, then what is? So some of the work that Mark and I have been working on has been on kind of getting away a little bit from the indices and looking at time series of wind stress and how they relate to the coastal sea level. And so we focused on 3 types of wind stress. We have remote equatorial forcing. So we just defined the average zonal wind stress over the equator within about 5 degrees of the equator. We also did local longshore wind stress in the vicinity of each tide gauge, and then the local wind stress curl as well. And so this has been done actually, I'm sure many of you know, in this region, but for interannual variability in the context of ENSO by Enfield and Allen and Shelton and Davis in the early 1980s. So we wanted to kind of extend what they did and look at longer term trends, in particular the recent trend, that flattening in the coastal sea level change there in the Northeast Pacific. So what we did was basically a regression analysis, similar to what Shelton and Davis did. There was some subtlety to what we did because there were some correlations between the wind stress time series, but I'm just going to breeze through that and just show you the results. So over here we have annual values of wind stress, and not wind stress, and sea level from 5 tide gauges: San Diego, San Francisco, Crescent City, Seattle, and Neah Bay. We also have, so for those sea level series, we removed the inverted barometer effect, and then we also, just like Mark showed earlier, we subtracted the Church and White reconstruction because we're interested in these redistribution signals and not so much the global uniform variability. And then we just did our regressions, and the red line is the sum of those wind stress time series, and I got these from INSET, by the way, multiplied by their regression coefficients. And you can see that we do pretty well. There, we get a lot of the interannual variability as well as some of the lower frequency variability. I've highlighted this recent period. You can see that there's a trend in the sea level, and it's accounted for fairly well by the wind stress time series. Okay, so this just kind of breaks that down a little bit into the different contributions from the various types of wind stress forcing. We have a bar plot here that shows the fraction of variance. This red bar shows the fraction of variance accounted for at each tide gauge by all of the wind stress time series put together. You can see we get greater than half the variance for all of them and up to even close to 70% for Crescent City. But what's interesting is that if you look at these individual contributions, this yellow bar, these yellow bars are for the equatorial wind stress. They account for most of the variance of these southern stations. If you look at the more northern stations here, the longshore wind stress becomes important, equally as important, if not more important, than the equatorial wind stress. And that's consistent with what Shelton and Davis and some of those other guys found before. But then if we look at the recent rate, what accounts for the recent rate of change over the altimeter period, and it's pretty consistently due to the equatorial wind stress. Despite the fact that a lot of variance is accounted for by the longshore wind stress, it doesn't account for much of the trend. So the long-term variability here appears to be more equatorially forced and similar to the variability in the Western Tropical Pacific that Mark discussed due to the trade wind variations. And so that seems to be a similar situation here in the coastal sea level. And so then you might expect then that if you look at perhaps the SOI, as Mark was saying, was a much better indicator of the trade wind forcing at the equator, then you would expect there to be a better correlation with the sea level. And indeed there is. I mean, there's not many degrees of freedom here, but the correlation is twice as large as it is with the PDO. So just to kind of sum up what Mark and I both were saying, I think together, is that the decadal variations in the trade winds, that equatorial forcing, that's the dominant driver of the long-term sea level change along the waveguides, the equatorial and the coastal waveguides in both the west and in the east. The local wind forcing can be an important driver of interannual variability north of San Francisco, but obviously the long-term variability we found was more related to the equatorial forcing. And so the PDO can be a useful predictor of sea level along these waveguides during the period when SOI and PDO are similar, such as Mark pointed out. But if you want to look at the whole 20th century, it appears that, at least of these coastal waveguides and along the equator, the SOI is probably a better indicator of what's going on in long-term sea level.